And it's nice to see many happy faces. I can't attribute to the weather, maybe it's the breakfast that was so awesome, but I hope to keep you happy through this next 1 hour. What I'm going to talk about is time synchronization, security, and smart grids. And you may wonder why I talk about that, since you are mostly interested in peer-to-peer energy trading and probably sustainability, because that's the promise that peer-to-peer energy trading would bring. You can use renewables in a more efficient, flexible manner than we do it today. Now, I would argue that when you talk about peer-to-peer energy trading, you would still have to deal with a physical system. The electric power system is actually a physical system. It's laws of physics that govern it. And ultimately, if you want this peer-to-peer energy trading to work, you have to make sure that your system is stable. It has to be safe all the time in a power system sense, so in a physical sense. And there is actually a lot of work going on in this area, both inside peer-to-peer energy trading and outside of it. So there is a lot of work on making the power system more efficient and more sustainable. How do we do that? Well, we try to characterize the system components in a better way, let's say more accurately. We try to get better models of the entire system. We try to introduce estimation that works in real time, so we are actually aware of the actual state of the system, which means we can take better controls and we can use the available energy resources more efficiently. This is one aspect. And then there is the other aspect, which is reliability. How do we make the system work more reliably? And there we can, for example, monitor the voltage in the system between any 2 points in real time, observe whether the voltage is within the bounds that we want it to be within. And there are many other applications that make the system more reliable. Now, how do we do it? There is a key technology that has emerged over the past 20 years, and that's called phasor measurement units. How many of you have heard about phasor measurement units? Okay, that's a fair bit. Great. So this figure shows the deployment of PMUs, as they are called for short, in the US a couple of years back. It's about 1,000 of them, actually much more than 1,000 of those deployed. I have a similar figure for Italy. Interestingly, for Europe, it's much more difficult to get figures. So this is Italian deployments of PMUs about 10 years ago, a little bit more than 10 years ago. You see, they are actually being deployed. I know also that Norway has lots of PMUs. There is some interference probably with the mics. I have a phone here. I can leave it here. I can leave it here. Yeah, let's put it here. Norway has lots of PMUs deployed because Norway, you know, is a very elongated country, and that makes the management of the power system actually challenging. So they have PMUs and they use those for monitoring in real time, but they don't use it for control in real time because actually in the power system industry, nobody trusts PMUs yet. The technology is not mature enough to be trusted because you basically trust the entire nation's economy in the hands of the PMUs if you rely on those for real-time control. So we have to make PMUs more trustworthy. Now, what is a PMU? A PMU measures synchrophasors. How many of you know what a synchrophasor is? Okay, a little bit less. Now, let's take a very simple power system as an example. This power system consists of 2 buses and the line between them. We can call it a transmission line. Now, if you look at these 2 buses, there will be a voltage at one bus and the voltage at the other bus. Let's call them bus 1 and bus 2. The voltage at bus 1 has always a magnitude that will change over time, right? It's an AC system. How do we describe this signal? We describe it by a sinusoidal. Now, from elementary school or maybe high school math, you remember how do we characterize a sinusoidal? Let's say a sinus. By the magnitude and by the phase, right? So we can characterize the voltage at bus 1 using its magnitude and its phase, and the same at bus 2. Now, how can we actually measure the phase of these sinusoidals at different points in a system? What do we need for that? We need a common reference. If we have a common reference, which we say this is phase 0, then we can tell what's the phase relative to the reference at bus 1 and at bus 2. How do we obtain this common reference in a system that spans maybe 3,000 kilometers? Well, by introducing accurate time synchronization. How accurate does this time synchronization have to have? I can give you some numbers. There is a standard, the IEEE 337-118 standard, that kind of mandates how accurate PMU measurements have to be. And it says that the total vector error has to be within 1%. What's the total vector error? The total vector error is, if you look at this illustration here, assume that this vector is our voltage phasor, the actual one that we would like to measure. Total vector error of 1% means that the value that we measure has to be within a circle that has a radius of 1% of the length of this vector. And that's what we have to measure. So we have to measure a quantity in here. It cannot lie outside. This is the 1% total vector error. Now, where do errors come from? Well, we can have an incorrect measurement of the magnitude of that vector, the length, or the angle. Where does the magnitude error come from? It comes from the transformation when we transform from a high voltage signal to a low voltage signal, which we can actually measure. Where does the angle error come from? It comes from time synchronization. If you don't have correct time, you don't have the correct angle because your reference is not correct, right? So if you assume that the magnitude measurement is correct, so there is no error in the magnitude, and you assume that all the error comes from time synchronization, then this 1% requirement in a 50 Hertz system means that your time synchronization has to be accurate to 30 microseconds over a huge geographical area. Now, in practice, you would require about 1 microsecond accuracy for time synchronization for PMUs. So this is the budget that you have. So each of the clocks of the PMUs has to be accurate to a common time reference within 1 microsecond. Now, how do you get that? There are commercial technologies that can provide this. You have all heard of GPS, right? Or global navigation systems. They don't only provide you the location, they also provide you very accurate time synchronization down to about 10 to 40 nanoseconds accuracy, which is actually pretty good for PMUs. There is also an alternative, and that's called network-based time synchronization. And the de facto standard today is IEEE PTP-v2. It's the Precise Time Synchronization Protocol, version 2 of it. Now, how does it work? It's a very simple scheme. The basic problem is, if I take a timestamp here, I put it in a message and I send it to you, by the time you receive this message, the time is not what I put in this timestamp, right? And actually, it's very hard to know how long it takes for a packet to travel through a network. So what do? Well, we do as best as we can. And that is the following. Imagine you have here a master clock, which is basically the clock that you want to synchronize to. And you have a slave clock here at the left. The slave clock would like to synchronize to the master clock. Now, what do? What we do is that we measure the time it takes to send a message to this intermediate device, a switch, we call it a transparent clock, and get it back. This is the round trip time between the slave and this intermediate device. We can do the same measurement between this intermediate device and the master clock. Then we have the round trip time here on this second link. Now we make an assumption. We assume that the delays are symmetric. What that means is that the time from the intermediate device to the slave clock is half of the round trip time, and the same holds for this propagation time. Now we have an estimate of the time it takes for a message to go from the master clock to the transparent clock and from the transparent to the slave. Next thing what we do is we send the message from the master clock with a timestamp to the transparent clock. Transparent clock adds the time it knows a message would take to travel over this link. And then it forwards the message, and then the slave clock compensates again with this one-way delay that it knows of. There is one more thing that we have to take care of. You know, these devices, they include lots of queues and processing. So we actually have to measure how much time a message spends within the device itself. So the time between the device receives the message and between it forwards this message to its, in this case, final destination. How can we do that? Well, we need actually hardware that supports timestamping. So we need hardware that supports timestamping in the circuitry. And if we have that, then using PTP, we can achieve an accuracy down to about 100 nanoseconds in a large-scale network, multi-hop network, which is, again, pretty good, and it's enough for our purpose. So these are the two technologies that today you can use for synchronizing the PMUs. Now, let's put PMUs into a bigger context. Have you seen this mnemonic OODA before? It's the military term for closed-loop control. It's observe, orient, decide, act. So you observe the environment, the enemy, you orient, you figure out what's going on, what do they want to do, then you take a decision, and then you implement it. And this basically, it's what we call in engineering closed-loop control, right? We measure, we estimate, then we use an algorithm to compute what to do, and then we have actuators that will act. So, but in a more strategic context, it's called the OODA loop. Now, how does this loop look like? Here we have a simplistic representation of an electric power system. The system is or can be described by its state. We will denote it by X. So X will be the state. And the state is actually the voltage phasors at the buses of the power system. So that's the quantity that if we know it, then we know kind of everything about our power system that is of interest. Now, problem, we cannot actually observe directly this state, but we can take measurements using these PMUs. What do we need for these measurements? As we discussed, we need a time reference, right? Now, what is the measurement? The measurement is a linear transformation of the actual state. Age is a matrix, so it's H times X, plus a noise term. And we often assume that this noise is Gaussian. Now, what can you do with these measurements? Well, one thing you can do is that you take them directly and you act on them. That could be a certain application. Say, voltage separation monitoring. You could be a little bit more clever and you could feed these measurements into a state estimator. I will talk later about what a state estimator is. It basically tries to remove the noise from the measurements. Yeah? Together with this estimator, you can have a bad data detector that checks for the consistency of the measurements. So it will tell you if some measurements are clearly outlying and you should just discard them. So now from the state estimator, you kind of get a sanitized estimate of the actual state X, and that we call X hat. And based on X hat, you can also reconstruct what you should have measured based on this system state as H times X hat. That would be Z hat. So that's what you should have measured if this had been the state. And now you can use these values to actually act upon the system. Now, you act upon the system, that's going to be your control signal that goes to the system, and that will then change the state of the system, and then you measure again, and this goes on forever, right? That's basically closed-loop control. That's all good, but what can go wrong here? Well, all this, because of the PMUs, relies on time. If time is corrupted, the entire system is corrupted, potentially. And today we are here to understand if this is actually the case and what can we do about it. So how can we actually secure the system against such a compromise? So we have a number of questions we would like to answer. First, could an attacker actually compromise the time references of PMUs? That's the first question. If not, then we can have coffee immediately in 5 minutes. If the answer is confirmative, then the second question is, could it happen that an attack remains undetected in the system? So it can have actually impact before it's detected. Again, yes, coffee, no, we stay here and listen. Third, is such an attack easy to compute? And last, okay, but does it actually have an impact? If it doesn't have an impact, we shouldn't worry about it because it's just there, but it doesn't cause harm, so who cares, right? So let's see the first question. Well, GPS is known to be vulnerable to attacks. Spoofing attacks are very well documented. They have been demonstrated even in real life on the Mediterranean, I think close to the coast of Italy. A big yacht was overtaken by people from actually, I think it was UT Dallas who demonstrated this. So they spoofed the GPS signal and they slowly made that the yacht would actually turn away from its intended course because the GPS told it that it was going straight, but it was not. So this you can do, and you can do the same thing with the time synchronization. So you can fool a GPS receiver into believing that the time is different than what it actually is. It of course takes some hardware, but actually not that much. You can buy this live SDR online, and if you know how to program it, well, you can do it. There is actually a more peaceful application of GPS location spoofing. If you are into Pokemon Go, you can fake your phone to be on the top of the Mount Everest and collect a Pokemon there, even though your phone is in your pocket. Yeah, so you can actually do GPS spoofing in practice. That works. Actually, GPS is not very reliable either. It was just a few years back in 2016 that GPS had suddenly an offset of about 13 microseconds. And this error persisted over a couple of hours. And it was not discovered by the US military, but actually by power systems operators, for example, in Finland. So such an error would also cause havoc in a system where PMUs are deployed and they depend on GPS. Is PTP any better than this? Well, unfortunately, no. So if you look at PTP and you remember the way it worked, if you inject messages in the network when these round-trip times are measured, or if you modify the packets that are sent between the master clock and the transparent and the slave, you can easily modify them. Why? Because PTP version 2 has no security controls. There is no message authentication. It's not possible. Now, what else can go wrong? Well, an attacker could compromise one of these transparent blocks. It's a router, it could be a Cisco router, and it could manipulate the messages that are forwarded through that transparent block. That would have the same effect. What can we do about this? Well, there is a new version of PTP that's called PTP version 2.1, which includes security controls. It has integrity protection using group keys. So what you do is you distribute the same key to every device in the network, and then they can use symmetric crypto to authenticate and to check message integrity. But we know that group key-based integrity schemes are not very strong because if an attacker compromises any of these devices, it has access to the group key and it can immediately manipulate all the messages that are transmitted in the network. Now, does actually this authentication affect the accuracy of PTP version 2.1? We made an experimental evaluation when the standard came out, and it seems like you can actually implement it in a way that it does not affect the accuracy at all. And even the computing overhead is actually tolerable. So you see here the processing times without security and with different flavors of security. There is a factor of 3 increase in the processing time, but that's still manageable with today's hardware. So computationally, this is actually feasible. Question is, does this actually protect against all kinds of compromise? And the answer is no, because what we do is we protect messages in flight, but we cannot protect them actually in transit within these devices when they are being processed. So an attacker that can compromise devices in the network could still manipulate time synchronization using PTP version 2.1. What could be a solution? For example, constant time crypto, but that does not exist today. It's very hard to make algorithms that have deterministic execution time on hardware in real life. So one may wonder if precise time synchronization and end-to-end security are actually compatible. I don't have the answer there. But I do have an answer to the first question. And there the answer is, yes, actually an attacker, if it wants to, it could compromise time synchronization for PM use. Second question, could an attack remain undetected? Well, this question so far is a little bit undetermined, because detected or undetected by what? Well, let's say by state-of-the-art schemes that are used in power systems today, and that's state estimation and bad data detection. So for that, we have to delve a little bit into not physics, but a little bit of linear algebra, not too much. How many of you have heard about weighted least squares estimation? Okay, a few. Okay, so to give you an intuition, imagine that you have a system whose state is a scalar. It's a real value. Yeah, it's a very simple system. So the state could be pi or 2 or 3, whatever, but it's a single value. Yeah? And from this system, you can take two measurements, Z1 and Z2. Z1 will always be twice this scalar value, the state, and Z2 will always be equal or should be equal to the state. Yeah? And you take these two measurements. Now, unfortunately, you live in real life, and every measurement you take is noisy. Yeah? So you have to live with the noise. And for this reason, when you take Z1, it's not actually going to be 2 times the state, but it's 2 times the state plus noise. And Z2 is 1 times the state plus noise. So you take these two measurements. Let's say that the measurement that you take is this Z prime there, up there. Oh? State estimation or estimation basically does the following. You know by math that basically your measurements should be on this blue line, right? Because Z1 should be twice Z2. Yeah? So you know that what you measure should be on the blue line. Now, in reality, it's not. What do? On the blue line, you look for the closest point to what you measured. Yeah? That's going to be this Z hat prime. And that's what you will say, I think this is what I should have measured. This is reality right now. The difference between Z prime and Z hat prime is what we will call the residual. That's the measurement error, basically, what you say. This is the measurement error. Yeah? So you take a measurement, you have a model of how the measurement is related to the state of the system. You have redundancy in the measurements, and this allows you to separate the measurement into noise and what you believe is the actual measurement, what it should be. Yeah? So this is the basic idea of state estimation. And then we can describe this in math. So we have a measurement model that says that the measurements we take, they should be age, a matrix, times the state plus noise. And state estimation is then a number of matrix multiplications. I think the details are not that interesting right now. And once you have this state estimate, you can also compute the residual. And what we should now remember is that this residual can be expressed as a matrix times the measurement you take. And we will call this matrix F. Yeah? So this will be our F matrix that allows us to compute the residual based on the measurements that we have taken. Yeah? So this is now the basic model of state estimation and bad data detection. Now, where is the bad data detection? Bad data detection would take these residuals. It would look at them. It would check if, for example, the largest normalized residual exceeds a certain threshold. If it does, you say that this measurement is an outlier. Let's discard it. And then we redo the estimation. Yeah? Now, let's look at our attacker model. Let's assume that the attacker knows the instantaneous measurements. It's a powerful attacker. It knows the system model, so the matrix H, and it can manipulate up to P time references. So for example, in this system, assume we have PMUs at these buses on the lines. So it could manipulate maybe P equals 3 time references, so the time references of these PMUs. So it can, remember, rotate the measurements taken at those PMUs. So it can manipulate these time references. Now, what is the impact of such a manipulation? You can express it by multiplying the complex measurement by a unit complex vector with the angle that corresponds to the time reference manipulation. So you have this voltage phasor, and the attacker can rotate the phasor. It cannot change the magnitude of the phasor, just can rotate it by a certain angle that it can pick actually. So this is our attack model. And now the question is, can the attacker manipulate time references without actually changing the residual? Remember, residual is computed as F times Z. So how would that work? When would an attack be undetected? It would be undetected if the residual computed based on the unattacked measurements and the residual computed based on the attacked measurements, attacked is Z plus delta Z, would be the same. Since this is a linear operation, this also means that F times delta Z would be equal to 0, right? So we are looking for an attack, a rotation, that would satisfy F times delta Z is equal to 0. Now, we can express this a little bit in a more complicated manner. We introduce an attack measurement indicator matrix that says if attacker manipulates a certain time reference, that will manipulate certain measurements. So it basically says which measurements are manipulated by which time reference. And then we can express the change of the vector as simply we take the rotation introduced on the first time reference times the measurement times this matrix and so on. And we add on all the P terms. So this is basically the condition that we have. The sum of these rotations multiplied by the matrix F times the measurements times this matrix that indicates the attacks should be equal to 0 for undetectability. This looks pretty ugly, but we can make it simpler. And we do so by introducing what we call the attack angle matrix. This is a Hermitian matrix, so it's a complex matrix. It's a P by P complex matrix, so it's fairly small actually. And the condition for undetectability will be then, if you take W, this matrix, and multiply it by the rotations of the attacker minus 1, that should be equal to 0. This is a very simple equation. Now, why is this equation not so simple? Because remember, here we work with complex values, and U is actually a complex unit vector. So this is a nonlinear system of equations. Is it easy to solve yet? Well, the answer is yes. If we use basic results from geometry from high school, then it is actually very simple. Why? Because, as an example, if you think of P equals 2, so 2 time references are compromised, then what you are looking for is the intersection between two circles in a complex plane. And that's fairly easy to compute, actually. Now, what do we learn from this? First thing, if the attacker can only manipulate one time reference, then there is no undetectable attack. That's good. If the attacker can manipulate two time references, then there is one non-trivial attack. So one attack that would not be detected by the bad data detector and is actually not 0. Is it good enough? Well, if you want to implement that attack, that would mean a jump in the system state. That may be detected with a dynamic state estimator. What if you have access to more than two time references? In that case, the attacker can actually implement a continuum of attacks. What that means is that the attacker can basically start from a zero attack and can gradually increase the attack up to the point that it desires to achieve. So then the attack is much more difficult to actually detect in practice. So bottom line, yes, attacks can be undetected. And if the attacker has access to sufficiently many time references, it can actually perform a continuum of attacks. Let's get back to our question list or list of questions then. So we have 3 yeses so far. Next question is, could an attack have significant impact? Now, what would be impact? For example, could you change the apparent power flow on a transmission line as it would appear to the operator? So what we did was we take a little bit into more details. There is a clock servo in these PMUs. I don't want to get into details about that. That's basically a PI controller. So you cannot introduce jumps in the clock in a PMU. What you basically do is you adjust the rate at which time elapses in the PMU. So the clock will go faster or slower in an attempt to make it align to the real time that it should have. Yeah? So actually the attacker, if the attacker is aware of that there is this PI controller, the attacker can adapt the input to the PI controller so that the output is what it wants it to be. And if the attacker is clever enough to do so, then what you see here is experimental results with such a clever attacker. And you see here the residuals in these plots. The leftmost plot is the residual without an attack, and the rightmost is the residual with an attack. I think you have to have really sharp eyes to notice the difference between these two. And you would in practice not notice the difference. What we can conclude is that this attack would actually remain undetected in practice. Okay, but does it have impact? What you see here is the apparent power flow between 2 buses in this example power system as a function of time. Time 0, the attack starts. These are 3 curves corresponding to different attack algorithms. And what you see is that the apparent power flow decreases from 1.5 to about 0.2. So basically the power flow disappears from the line. It did not disappear, it's there, but you don't see it. You as operator don't see it. No? Without the attack, it's the black curve at the top. That's the actual apparent power flow on the line. It's 1.4 time per unit. So the attack can have actually significant impact. Of course, this is just an example from this IEEE 39-bus power system, but you could construct similar examples on real power system topologies as well. So the attack can actually have a pretty big impact. Well, that's a little bit discouraging, or at least it's alarming. So what can we do about it? Well, we can think about new algorithms to detect such attacks. What's kind of the design space that we have? We have a cyber physical system. So we could try to detect the attacks on the cyber side. We could try to detect the attacks on the physical side. We could try to detect the attacks in a passive way, which means we do not interfere with the operation of the system. Or we could try to detect the attacks in an active way, when we perturb the system. And this has different names in the literature, right? Cyber and passive, that would be a traditional intrusion detection system, an anomaly detector or a signature-based detector. Passive, physical, that's state estimation and bad data detection. That's basically what's done today. Cyber active, that's typically what we call a moving target defense, where we change the system configuration over time so that it's difficult for the attacker to adapt. And then active and physical, that's what we call perturbation-based detection. Now, what's good about active detection is that it has a better potential to detect attacks. What is bad is that it affects the normal operation of the system. There is a price to pay for it. At least the system complexity will increase, manageability will become poorer, and actually in a power system you could lose millions of dollars if you deviate from the optimal operating point of the system. So there is a price tag to pay. So how can we then develop clever schemes for detecting these attacks? By realizing that actually we have a cyber physical system, so we can cross these boundaries in this case. Well, what would be first the detection problem? We can formulate it. Say we have measurements, complex measurements. We have m of those. And what we are looking for is a function that would map these measurements onto 0, 1. 0 meaning not attacked, 1 meaning attacked, compromised measurement. This would be a detector. Second problem is localization or identification. In this case, the problem is more complex. What you want to be able to do is you want to have a function that would map measurements into a binary vector that has the same number of entries as the number of time references, and you want to pinpoint which time references are actually corrupted. So you want to identify the source, the location of the attack. So let's look at these two problems. First, we look at detection for a single time reference. And here, one way to go is to look at the system as a cyber physical system, cyber being time synchronization, physical being what you actually measure. And the underlying hypothesis is that the attack would affect the correlation between the phasors, the phase angles, and the way they change over time, and the adjustments that you make to the clock in the PMU. So if there is no attack, this correlation has a certain pattern and a certain value. If there is an attack, it will have to be different, just because of the attack. Now, why is this hypothesis? If you look at this little plot here, what you see here is real and imaginary parts. So you see here a voltage phasor. If you take, let's say, a measurement that you should have taken, but you actually took the red one, where does the red one come from? Well, there is some measurement noise, and then there is the difference because of the attack. So this is how the attack comes about, or the actual measurement comes about. And this, over time, can be converted into a correlation metric. So we worked out an expression for the correlation between these two quantities, and then we use this to develop detectors. One detector is model-based. So if you know the parameters of your equipment and of the system, then you can go this model-based path. Alternative is to use machine learning. So you have a simple sequence of measurements, sequence of these correlation values. You train a classifier, and you use that for detecting malicious input. And what you see here is a receiver operating characteristic curve. Anyone familiar with receiver operating characteristic curve? Yeah, very good. So we have here false positives. That is basically the false alerts. You want to have 0 false positive. And here we have the true positive, which means the true alerts. So what fraction of alerts is actually good? There you want to have 1. So a good detector should be in the upper left corner. Now, what you see here, diagonal is basically random guessing. That's no good. The proposed detectors are up here in the top left corner. So they are actually pretty good. Of course, the evaluation is hypothetical. It's not in a real system. But still, they are much more efficient than what you could do with state-of-the-art, for example, with CUSUM, which is a typical change detector. Let's take a look at an alternative at the system level. This one is based on graph signal processing. The underlying idea is that the system state X, it lies in a low-dimensional space. So even though maybe in a 39-bus system, you have 39 state variables, these 39 state variables, they live in a subspace that maybe has a dimension of 20. Now we have to identify this subspace. Now, what is graph signal processing? How many of you know the Fourier transform? That's time signal processing, right? You have a time series and you convert it into frequency components. In graph signal processing, you have a signal on a graph, so there is a topology to your signal, not only the temporal dimension, and you convert this signal into something like components over this graph. And you do that basically based on the eigenvectors of the Laplacian of the graph, but that is not that important for now. So how can we use graph signal processing for detecting such attacks? Let's first look at conventional state estimation. We have already looked at that. So the system state there is basically this vector x, remember? And we have the measurement model, which was linear. And we have the residual, which we said was f times z. Now, in the case of graph signal processing, what we say is that x, the state, is approximately a low-pass graph signal. So we have low graph frequency components only. Well, how low? Well, that's a question. That would be this value k. But basically what this says is that we can express our actual state x as a low-pass graph signal. And this low-pass graph signal will be this x hat k. So the subscript k will denote that it's a graph signal. The measurement model is very similar as in the normal state estimation case, but now we have a modified system matrix hk. And the same holds for the residual. Now we have rk, and rk is simply fk times z. So it's the same expressions, it's just the matrices that will be somewhat different. Now, how can we use this for detection? Well, first, remember our original definition of undetectability said if the residual does not change due to the attack, then the attack is undetectable. We can have an alternative definition using graph signal processing where we say that if the residual using the matrix fk is 0, then this attack is undetectable using graph signal processing. What's the relationship between these two? Well, there is a one-directional implication. If an attack is k undetectable, then it's also undetectable. So detection using graph signal processing is in a way stronger than detection based on the normal residuals. So that gives some promise that actually GSP would be able to give us better detectors against these kind of attacks. So let's take a look at some results. What we did was we evaluated these detectors on this IEEE 39 bus system and on the 300 bus system and on the 2300 bus Polish system. These are big IEEE and non-IEEE test networks. And the evaluation metric is the area under the curve. Remember the ROC curve, false positive, true positive. You can integrate the curve that you obtain. That's the area under the curve. And that's a commonly used metric for quantifying how good a detector is. If the value is 1, the detector is kind of perfect. If it's 0.5, it's pretty good, pretty bad, sorry. Yeah? So this is the area under the curve. Now, what you see here in these 6 figures, on the left, you see attacks that are in principle easy to detect because they are not undetectable even with traditional state estimation. And on the right, in these 3 figures, you see attacks that should be difficult to detect because they are almost undetectable using traditional state estimation. Vertically, at the bottom, we have attacks that have a low impact on the system, so they have a small impact. At the top, we have attacks that have a very high impact. So they are the ones that are very important to detect, actually, because they could have an impact on the system. Now, what do we see here? Let's just compare 2. The one here, which is legacy state estimation-based detection using machine learning, and the one on the right, which is the proposed detector using the graph Fourier transform, so graph signal processing. So what you see here is that the AUC is close to 1 on the right. It's actually not that close to 1 on the left. This is for the attacks that are easy to detect. And then for the attacks that are pretty hard to detect, you see here an AUC of 0.52, which is basically random guessing using traditional methods, 0.85 using graph signal processing, and even 1 if we go higher, 0.5 down here. So there's a significant difference in the ability to detect attacks if you use traditional state estimation versus graph signal processing. So there is some prospect to doing detection by using alternate methods. Now, we have talked about detection. What else can we do to make the life of the attacker harder? Well, we could harden the system. Hardening could be, for example, through introducing security controls, changing system configuration, and so on. Let me just give you one example that is also kind of cyber-physical approach to hardening time synchronization security. How would that work? Well, the objective is to ensure detectability of attacks by changing the system configuration. So we want to be able to detect all attacks in the system. How do we achieve that? Well, we make it impossible to perform undetectable attacks against the system. All the others we can actually detect. So it's only the undetectable ones that we have to focus on. How could we achieve that? Well, one approach is to add more PMUs to the system. As you will see later, the more PMUs there are, the more robust is our system against attacks. The downside is that it's expensive to deploy PMUs. The alternative is to secure time references of the existing PMUs. So let's take a look at this second approach. We will call this the minimum cost mitigation problem for PTP. What do we have here? We have a graph of the underlying communication system for PTP. This is basically the network where time synchronization is happening. And what we want to do is we want to secure a minimal amount of network equipment. In this case, it's links and routers, in a way that will make these undetectable attacks impossible. And this is then equivalent to the problem of finding a minimal subtree such that at most two PMUs per equivalence class will be not included in the set of edges that we pick. Now, this is an NP-hard problem. I will not really go into details how to solve it. You can approximate it. You can always develop a greedy algorithm that's in some way, for example, constructs paths to PMUs and then extends these paths to include other PMUs in a cost-efficient manner. Alternative is to realize that this problem is the same as the Graf-Steiner tree problem, which is a known combinatorial optimization problem. And there are approximation schemes for that. So what you see here is some numerical results. Horizontal axis is the number of deployed PMUs in the system. So you see that goes from about 100 to about 500. And you see the vertical axis is the mitigation cost. And curves correspond to two different power systems, the 118 bus system and the 300 bus system. And what you see is that the mitigation cost decreases sharply as the number of deployed measurements increases in the system. So there is really such a trade-off between how many PMUs you have in the system and how much you have to invest in security controls to make your system not vulnerable against time synchronization attacks. If you compare the results for the different algorithms, you see that there is, well, kind of a significant gap between the cost if you use different algorithms, up to 20%. In terms of computational time, well, computational time is feasible, order of hundreds of seconds. Even for a big system, in a few thousands of seconds, you can actually compute the best way to secure the system. So there is prospect to actually mitigate these attacks. We have talked about detection. We have talked about hardening. Now there is one more step left. And that's somewhat more complex, you could argue. And that would be to understand the actual motivation and the behavior of the attacker. Why? Because if you understand the behavior and the motivation of the attacker, you can make much more efficient defense schemes and response schemes against the attacker. And this leads us into the realm of game theory. And you can apply this also to, say, peer-to-peer energy trading. Why or how would an attacker want to compromise a peer-to-peer energy trading system? How could it do so? For example, the attacker could use a time synchronization attack to manipulate our view of the system state, in which case peer-to-peer energy trading, if implemented as planned, would actually lead to an unstable system and the system collapse. What else could an attacker do? An attacker could also go directly against stability. It could manipulate, for example, the flexibility offers. Right? You could announce that you will decrease your consumption by 200 megawatt tomorrow. Someone takes it for granted, but then you actually don't do it. Or you come up with a more sophisticated scheme, result either system collapse or a significant increase in the cost of operation because you have to somehow compensate for this loss of flexibility. So to summarize, I would argue that renewables, and including their peer-to-peer energy trading, they basically make it ever more important to focus on grid stability. No matter if you have a microgrid or if you have an over-the-grid operation, in whichever phase you are, you have to make sure that the system is actually stable. And for that, you have to implement monitoring and real-time control solutions. And for real-time observations, you will probably have to rely on technologies such as those that I was talking about. So you will have to look more into real-time control of the grid and real-time situational awareness. The more controls you introduce into a system, the more flexibility it has, the bigger the attack surface, and the more complicated are the attack vectors. And you have to understand those. And you have to understand which ones are actually dangerous, which ones are easy to do, and which ones would an attacker want to actually perform. And you have to harden your system against those attacks. And when doing so, I would also argue that it's important to take into account the fact that the power system is actually a physical system. There is physics underlying, and you can use it for your own benefit, actually. And that's something I think that's very important. With that, I would like to acknowledge my collaborators from KTH, PhD students and postdocs, colleagues from APFL with whom we worked on this topic, and colleagues from Siemens. And I thank you for your attention. If you have any questions, I'm very happy to take those.